Welcome to this scientific lecture on porous nanomaterials and their revolutionary role in thermal regulation of buildings. Today we will explore how these advanced materials prevent unwanted heat transfer in both summer and winter. Buildings face a constant thermal challenge. During summer, external heat tries to enter our homes. During winter, internal heat tries to escape. Traditional insulation has limitations, but porous nanomaterials offer a breakthrough solution. You might ask, what makes this a problem worth solving? Well, heating and cooling account for approximately 40% of total energy consumption in residential buildings. Reducing this would have enormous environmental and economic impacts. Here we see a simplified representation of a building. Red arrows show heat entering during summer, blue arrows show heat escaping during winter. Our goal is to block both. Before we discuss applications, we need to understand what porous nanomaterials actually are. These are materials with nanoscale pores, typically ranging from 1 to 100 nanometers in diameter. What exactly is a nanometer? A nanometer is 1/1000th of a meter. To put this in perspective, a human hair is approximately 80,000 nanometers thick. We are talking about structures at the molecular scale. 1 nanometer equals 10 to the -9 meters. The pore sizes we are discussing range from 1 to 100 nanometers. This diagram shows a simplified cross-section of a porous nanomaterial. The green circles represent nanoscale pores distributed throughout the solid material. The porosity can range from 50 to 99% of the total volume. To understand how porous nanomaterials work, we must first review the three fundamental mechanisms of heat transfer: conduction, convection, and radiation. Conduction is heat transfer through direct contact. When molecules vibrate, they transfer kinetic energy to neighboring molecules. This is how heat travels through solid materials. The heat flux Q equals negative Ka times dt over dx, where K is thermal conductivity, A is area, and dt over dx is the temperature gradient. This is Fourier's law of heat conduction. Heat flows from hot to cold regions. The yellow arrows represent the direction of heat flow through the material via molecular vibrations. Convection is heat transfer through fluid motion. When air or liquid moves, it carries thermal energy with it. This is why wind makes you feel colder on a cold day. Radiation is heat transfer through electromagnetic waves. All objects emit infrared radiation proportional to their temperature. This is how the sun warms the Earth across the vacuum of space. The radiated power Q equals sigma epsilon AT to the fourth power, where sigma is the Stefan Boltzmann constant, epsilon is emissivity, A is area, and T is absolute temperature. Now let us examine how porous nanomaterials reduce conduction, which is typically the dominant heat transfer mechanism in building materials. You might wonder, why is air such a poor conductor? Air molecules are far apart compared to molecules in solids. This means fewer collisions and less efficient energy transfer. The thermal conductivity of air is approximately 0.026 watts per meter Kelvin. Compare this to glass, which has a thermal conductivity of about 1 watt per meter Kelvin. Glass conducts heat 40 times more efficiently than air. The key insight is this: by creating nanoscale pores filled with air, we maximize the proportion of poorly conducting air while minimizing the solid pathways through which heat can flow. On the left, we see traditional material with continuous solid pathways allowing efficient heat conduction. On the right, the porous nanomaterial forces heat to take a tortuous path through both solid and air, dramatically reducing heat flow. You might now ask, if the pores are filled with air, won't convection occur? This is an excellent question, and the answer reveals another benefit of nanoscale pores. What prevents convection in tiny pores? Convection requires bulk fluid motion, which needs space. When pore sizes become comparable to the mean free path of air molecules, convection becomes impossible. The mean free path of air molecules at standard temperature and pressure is approximately 68 nanometers. When the pore size is less than or comparable to the mean free path, air molecules collide with pore walls more often than with each other. This prevents the coordinated bulk motion needed for convection. This phenomenon is called the Knudsen effect, named after physicist Martin Knudsen. It essentially traps air molecules in place, eliminating convective heat transfer. In large pores on the left, air molecules can move collectively, creating convection currents shown by blue arrows. In nanopores on the right, molecules shown as blue dots are essentially frozen in place by constant wall collisions. The third mechanism we must address is thermal radiation. Traditional insulation is often transparent to infrared radiation, allowing radiative heat transfer to bypass the material entirely. How do nanomaterials block infrared radiation? This is where the nanostructure becomes crucial. When pore sizes are comparable to infrared wavelengths, multiple scattering occurs. Infrared wavelengths range from approximately 3 to 15 micrometers, which is 3,000 to 15,000 nanometers. Here is a useful analogy. Nanostructures scatter infrared radiation the same way tiny water droplets in fog scatter visible light. The radiation bounces around randomly, and most of it gets reflected back rather than transmitted through. The transmission T equals e to the negative tau, where tau is the optical thickness. Greater scattering increases tau and decreases transmission exponentially. Now let us examine specific examples of porous nanomaterials used in building applications. The most famous example is silica aerogel, sometimes called frozen smoke. What makes aerogels so special? Aerogels have porosities exceeding 99%. They are essentially solid air. Their thermal conductivity can be as low as 0.013 watts per meter Kelvin. This is approximately half the thermal conductivity of still air, making aerogels the best solid insulator known. This represents the structure of silica aerogel. The white lines show the silica framework, which occupies less than 1% of the volume. The rest is nanopores filled with air. One exciting application is aerogel glazing for windows. Traditional double-pane windows have an R value of about 3. Aerogel-filled windows can achieve R values of 20 or higher. What is R value? R value measures thermal resistance. Higher R values mean better insulation. It is defined as thickness divided by thermal conductivity. R equals L over K, where L is thickness in meters and K is thermal conductivity. Aerogel windows can be 5 times more insulating than standard windows, while maintaining approximately 75% visible light transmission. This means they stay transparent while providing exceptional insulation. On the left is a traditional double-pane window with an air gap. On the right is an aerogel glazed window. The blue tint represents the aerogel filling, which provides dramatically better insulation. For walls, aerogel insulation boards offer similar benefits. A 10 mm thick aerogel board can provide the same insulation as 50 mm of traditional foam insulation. The ratio of 10 mm aerogel to 50 mm foam equals the ratio of their thermal conductivities, approximately 0.04 divided by 0.013, which equals about 3. This space saving is crucial for retrofitting existing buildings where interior space is valuable. You can add high-performance insulation without significantly reducing room size. Another advanced technology combines porous nanomaterials with vacuum technology. Vacuum insulation panels, or VIPs, use a nanoporous core surrounded by a vacuum-sealed barrier. How does vacuum improve insulation? By removing air molecules, you eliminate both conduction through air and convection entirely. Only radiation and solid conduction through the core structure remain. VIPs can achieve thermal conductivities as low as 0.004 watts per meter Kelvin, approximately 1/6 that of air. The nanoporous core serves a critical structural function. It prevents the panel from collapsing under atmospheric pressure while maintaining the vacuum. Without it, the panel would compress and lose all insulating value. This cross-section shows a vacuum insulation panel. The gray outer layer is the sealed barrier. Inside is the nanoporous core, shown in brown with blue pores. The vacuum space surrounds the core structure. Let us now quantify the potential energy savings. Consider a typical house with 100 square meters of exterior wall area in a climate with 2,000 heating degree days per year. What are heating degree days? This is a measure of how much heating is required. It is the sum of degrees below a reference temperature, typically 18 Celsius, over a year. The annual heat loss, Q, equals A times delta T times days divided by R, where A is area, delta T is temperature difference, and R is thermal resistance. For traditional insulation with R value of 2.5 square meter Kelvin per watt, Q traditional equals 100 times 20 times 365 divided by 2.5, which equals approximately 292,000 megajoules per year. For aerogel insulation with R value of 10 square meter Kelvin per watt, Q aerogel equals 73,000 megajoules per year. This represents a 75% reduction in heat loss. For a typical household, this could save several $100s annually in heating costs. Despite these impressive benefits, porous nanomaterials face several challenges that have limited widespread adoption. First is cost. Aerogel insulation can cost 10 to 15 times more than traditional fiberglass insulation per square meter. While life cycle costs may favor aerogels due to energy savings, the upfront investment remains a barrier. Second is mechanical fragility. Pure aerogels are extremely brittle. They require careful handling and protective layers, which adds complexity and cost to installation. Third is moisture sensitivity. Many porous nanomaterials can absorb water, which dramatically degrades their insulating properties. Water has a thermal conductivity of 0.6 watts per meter Kelvin, much higher than air. Fourth is long-term degradation. For vacuum insulation panels, any loss of vacuum over time will cause catastrophic loss of insulating performance. The barrier must remain perfectly sealed for decades. Researchers are actively working on solutions to these challenges, and several promising developments are emerging. Hybrid aerogel composites combine aerogels with polymer matrices to improve mechanical strength while maintaining low thermal conductivity. These materials are more durable and easier to handle during installation. Hydrophobic surface treatments make aerogels water repellent. By chemically modifying the pore surfaces, water cannot enter the nanopores, protecting the insulating properties even in humid environments. Advanced getter materials in vacuum insulation panels absorb any gas molecules that permeate through the barrier, maintaining the vacuum for longer periods. Some manufacturers now guarantee performance for 50 years. Scalable manufacturing processes are reducing costs. As production volumes increase and processes become more efficient, prices are dropping. Some projections suggest costs could fall by 50% within the next decade. Let us examine some real-world performance data from buildings that have implemented these technologies. The Rock and Roll Hall of Fame in Cleveland used aero glazing in their windows. They reported a 40% reduction in cooling loads during summer while maintaining excellent natural lighting. A residential retrofit project in Germany used aerogel insulation boards in the walls. The measured heating energy consumption decreased by 65% compared to pre-retrofit values. A passive house in Switzerland incorporated vacuum insulation panels in the walls, achieving an annual heating demand of only 12 kilowatt-hours per square meter, far below the 15 kilowatt-hour threshold for passive house certification. This comparison shows energy consumption before and after retrofit with porous nanomaterial insulation. The dramatic reduction in energy flow shown by the smaller green arrow demonstrates the real-world effectiveness. One important consideration in practical applications is thermal bridging. Even the best insulation can be undermined if heat finds alternative pathways through structural elements. What is a thermal bridge? A thermal bridge is a localized area with higher thermal conductivity than the surrounding insulation, creating a preferential pathway for heat flow. Common thermal bridges include wall studs, window frames, and fasteners that penetrate the insulation. These can reduce overall wall R value by 20 to 30%. The effective R value is less than the insulation R value due to these bridges. Continuous insulation layers that cover structural elements minimize thermal bridging. This is where thin, high-performance materials like aerogel boards excel. They can be applied over studs as a continuous layer. Beyond energy savings, we must consider the environmental impact of manufacturing and disposing of these materials. Aerogel production requires significant energy and chemical inputs. The supercritical drying process is energy-intensive. However, life cycle analyses show that the embodied energy is recovered within 1 to 3 years through reduced heating and cooling energy. Silica aerogels are chemically inert and non-toxic. They do not offer gas-harmful compounds and are safe for building occupants. Some aerogels are even recyclable, though this is not yet widely practiced. The carbon footprint reduction from energy savings far exceeds the manufacturing emissions over the building lifetime. A typical installation can offset its embodied carbon within 2 years. To put everything in perspective, Let us compare the thermal performance of different insulation technologies at the same thickness. This table compares thermal conductivity and R values for 25 mm thickness. Aerogel provides 3 times the insulation of fiberglass. Vacuum insulation panels provide 10 times the insulation. Looking forward, porous nanomaterial insulation will be critical for net zero energy buildings that produce as much energy as they consume. Net zero buildings require exceptional insulation to minimize energy needs. The less energy needed for heating and cooling, the smaller and more affordable the renewable energy system must be. Combination with passive solar design creates synergy. High-performance windows with aero glazing can admit solar heat in winter while blocking summer heat gain through proper shading. Smart dynamic insulation is on the horizon. Researchers are developing materials whose thermal properties can be tuned electrically or optically, allowing buildings to adapt to changing conditions. Let me summarize the key concepts we have covered in this lecture. Porous nanomaterials exploit 3 mechanisms to block heat transfer. They minimize conduction by maximizing air content. They eliminate convection through the Knudsen effect. They scatter infrared radiation through nanostructure. Aerogels represent the state-of-the-art with 99% porosity and thermal conductivity as low as 0.013 watts per meter Kelvin. Vacuum insulation panels combine nanoporous cores with vacuum for exceptional performance, achieving thermal conductivity as low as 0.004 watts per meter Kelvin. Real-world applications show 65 to 75% reductions in heating and cooling energy, demonstrating the practical effectiveness of these technologies. Current challenges include cost, fragility, and moisture sensitivity, but ongoing research is addressing these limitations through composites, surface treatments, and improved manufacturing. Life cycle analysis confirms that environmental benefits from energy savings far exceed the manufacturing impacts, with payback periods of 1 to 3 years. Future applications in net zero buildings and smart adaptive insulation systems will be transformative for building energy efficiency. In conclusion, porous nanomaterials represent a revolution in building science. By manipulating matter at the nanoscale, we create materials that outperform anything nature or traditional engineering has produced. These materials address one of humanity's greatest challenges, reducing energy consumption and greenhouse gas emissions from buildings, which account for nearly 40% of global energy use. The physics is elegant. Use air itself as insulation, trap it at the nanoscale where molecular physics changes the rules, and block all 3 heat transfer mechanisms simultaneously through carefully designed nanostructure. As costs decrease and performance improves, widespread adoption is inevitable. Within the next 2 decades, porous nanomaterial insulation may become as common as fiberglass is today. This technology exemplifies how fundamental materials science research translates into practical solutions for global challenges. From laboratory curiosity to building revolution, nanomaterials are reshaping our built environment. Thank you for your attention. I hope this lecture has given you both a deep understanding of the science behind porous nanomaterials and an appreciation for their transformative potential in building energy efficiency.